with the increased solar flares risk. Sunspot AR3664 has rapidly become a focal point for scientific scrutiny. This colossal sunspot, one of the most active and sizable of this solar cycle, is now at the forefront of discussions about space weather's potential impacts on Earth. In this video, we will delve into the science of this specific sunspot, explore its similarities with historic solar events like the Carrington event of 1859, and see if a similar event like Carrington took place today. How will it impact us? In the vast expanse of our solar system, the sun reigns supreme, its fiery heart sustaining life on Earth. Yet even within this colossal sphere, there are regions that stand out, exhibiting extraordinary power and activity. Today we delve into one such phenomenon, AR3664, a solar behemoth. Active region 3664, or AR3664, is a designation given to a particularly intense and dynamic area on the sun's surface. Active regions like AR3664 are characterized by complex magnetic fields that can unleash powerful solar flares and coronal mass ejections, sending charged particles hurtling into space. These regions often harbor sunspots, cooler, darker areas on the sun's surface where magnetic fields are exceptionally strong. AR3664 is no exception. Within its confines, sunspots cluster, each one a manifestation of magnetic turbulence. The study of active regions like AR3664 is crucial for understanding the sun's behavior and its impact on the solar system. Solar physicists monitor these regions closely, utilizing telescopes and space-based observatories to gather data. This information helps predict space weather events that can affect Earth, from disrupting communications to endangering satellites and astronauts. Solar physicist AR3664 has been particularly intriguing because of its size and activity. It has produced several significant solar flares, each releasing massive amounts of energy. By studying the magnetic configurations and changes within AR3664, we gain insights into the mechanisms driving these powerful eruptions. Solar flares from regions like AR3664 can have profound effects. When these energetic particles reach Earth, they interact with our magnetosphere, leading to phenomena such as auroras, beautiful yet potentially disruptive to technology. While auroras paint the night sky with mesmerizing colors, the underlying solar activity poses real challenges. Geomagnetic storms can impact power grids, GPS systems, and radio communications. Understanding and predicting these events is a priority for space weather forecasters. The data gathered from AR3664 helps refine our models of solar activity. By analyzing its behavior, scientists enhance their predictive capabilities, aiming to mitigate the effects of space weather on our increasingly technological society. AR3664, like all active regions, reminds us of the sun's dynamic nature. It is a testament to the immense energy at play within our star, influencing not just our planet, but the very fabric of the space around us. Sunspots are cooler areas on the sun's surface formed by intense magnetic activity that inhibits convection. These magnetic fields can become twisted and sheared, leading to sudden releases of energy known as solar flares. AR3664 has been particularly prolific, producing multiple M-class and even X-class flares. These powerful eruptions send bursts of electromagnetic radiation across the solar system, which can be observed on Earth as sudden increases in radiostatic or disruptions in communication and navigation systems. This sunspot has also been associated with several coronal mass ejections. These spectacular solar events occur when large bubbles of gas and magnetic fields are ejected from the sun's corona, depending on their path through space. These CMEs can collide with Earth's magnetic field, sparking geomagnetic storms that can disrupt power grids and satellites. The recent activities of this sunspot remind us of our star's potential to affect modern technology profoundly. This potential for disruption underscores the importance of monitoring sunspots like this one. Scientists use a variety of tools, including space-based observatories, like NASA's Solar Dynamics Observatory and ground-based solar telescopes, to keep a close eye on these features. By studying the growth, movement, and magnetic properties of this sunspot, researchers can better understand the processes that lead to solar flares and CMEs. This knowledge is crucial for improving predictions of space weather events, which in turn helps to protect satellites, power networks, and other critical infrastructure from the sun's unpredictable temperament. Observatories and science centers around the world are leveraging this rare event to teach people about the sun's dynamic nature and its effects on Earth through projected images on sidewalks or screens. Even those without a telescope can watch. As this specific sunspot rotates with the sun and changes over days. As we approach the peak of the sun's 11-year activity cycle, the insights gained from monitoring this sunspot are crucial. Observing and studying it underscores the importance of these celestial phenomena and their significant impact on our technology-dependent world. The Carrington event of 1859, named after astronomer Richard Carrington, stands as the most potent geomagnetic storm ever recorded, triggered by a colossal solar flare that hit Earth's magnetosphere. The relevance of this historical event to our modern understanding of solar activity cannot be overstated, especially as we observe the activities of sunspots like AR3664. Similarities between the Carrington event and the recent behaviors of this sunspot provide a stark reminder of the sun's capacity to disrupt Earth's technological fabric. When Carrington observed the flare that bears his name, it took less than 18 hours for the resultant geomagnetic storm to reach Earth, highlighting the speed and impact of solar ejections. Telegraph systems across Europe and North America failed, with operators reporting spies leaping from their equipment, some severe enough to start fires. Today, Arkansas's 3664 mimics this historical behemoth, showcasing intense flares and CMIs capable of similar, if not more severe, technological disruptions due to our increased reliance on electronic systems and satellites. In the wake of the Carrington event, auroras typically seen only near the poles were witnessed as far south as Cuba and as far north as Queensland, Australia, painting a stark picture of the geomagnetic forces at play with AR3664. Recent activity scientists and researchers have heightened their monitoring, recognizing that the vivid displays of auroras signify vast and powerful movements in Earth's geomagnetic field that could herald broader electronic disturbances. The culture and scientific significance of the Carrington event continues to resonate today, as it serves as a benchmark for what we might expect from current solar activity. Discussions about AR3664 in academic and public spheres reflect several concerns, with the potential for internet apocalypses or widespread blackouts often headlining discussions. Modern society's infrastructure, finely tuned and highly dependent on stable magnetic conditions, remains vulnerable to solar storms of the magnitude seen in 1859. The strategies developed post-Carrington, ranging from hardened electrical grids to satellite shields, illustrate ongoing efforts to mitigate these vulnerabilities as we move forward. The lessons learned from observing this spot are integrated into global preparedness plans. International bodies like the United Nations Office for Space Affairs and the International Space Weather Initiative work tirelessly to enhance the collaborative tools necessary to predict and mitigate the impacts of space weather. Imagine a modern-day Carrington event. The consequences would reach far beyond beautiful oral disciplines displays, potentially crippling the global economy and disrupting daily life. This scenario isn't just a theoretical worry. Despite these dire predictions, advancements since the 19th century have left us better equipped to handle such challenges. Today's researchers use sophisticated models to predict solar activity and its potential impacts. Agencies like NASA and NOAA operate fleets of solar observation satellites that provide real-time data crucial for early warning systems. Internationally, policies and protocols are being developed to respond to severe space weather events. Exercises simulating large-scale solar storms are conducted to test the resilience of national and global infrastructure. These efforts are crucial in building a response framework that could help minimize the chaos of a Carrington-level event. In conclusion, as AR3664 reminds us of our star's formidable power, it also emphasizes the importance of resilience and innovation in safeguarding our interconnected world. The observation and study of AR3664 not only offer insights into the physics of our sun, but also act as a reminder of our vulnerability to the vast forces of our solar system. Through continued vigilance and scientific inquiry, we aim to ensure that, even if history repeats itself, we are far better prepared to handle its challenges than ever before. By understanding these powerful solar phenomena, we can better prepare for their impacts and safeguard our technology-driven society. Thank you for joining us as we explored the dynamic and potentially disruptive world of sunspot AR3664. By understanding these powerful solar phenomena, we can better prepare for their impacts and safeguard our technology-driven society. Keep watching the skies and stay curious about the wonders of our solar system.